Hello everyone, welcome back to the channel. Today we begin a long and deep journey into one of the most elegant and powerful ideas in physics, the path integral formulation of quantum mechanics. This formulation was introduced by Richard Feynman, and it gives us a completely new way to understand how quantum systems behave. Instead of thinking only in terms of wave functions and operators, we imagine that nature explores every possible way a system can evolve. And the result we observe comes from adding up contributions from all those possibilities. To understand why this idea is so revolutionary, let us first recall how motion is described in classical physics. In classical mechanics, a particle moves along a single well-defined path. If you know its initial position and velocity, and if you know the forces acting on it, then in principle you can predict its entire future trajectory. This path is determined by Newton's laws, or in a more elegant form by the principle of least action. The principle of least action says that out of all possible paths a particle could take between 2 points in time, the actual path taken is the one for which the action is stationary. Usually a minimum. The action is defined as the time integral of the Lagrangian, and the Lagrangian is the difference between kinetic energy and potential energy. Quantum mechanics challenges this picture at a very deep level. Instead of definite trajectories, we talk about probability amplitudes. Instead of certainty, we talk about likelihoods. But even in the standard formulation of quantum mechanics, we still often imagine particles evolving smoothly according to the Schrödinger equation. The path integral formulation pushes this idea further and says something much more radical. It says that a quantum particle does not choose a single path. Instead, it explores every possible path connecting the initial point and the final point. Straight paths, curved paths, wildly zigzagging paths, even paths that loop back and forth. All of them are included. This does not mean that the particle literally travels along all these paths in a physical sense. Rather, this is a mathematical way of computing the probability amplitude for the particle to go from one point to another. For each possible path, we associate a complex number and then we add all these complex numbers together. The final result of this sum is the probability amplitude for the process. The key quantity in this formulation is the action. For a given path, the action is a number that measures how much kinetic and potential energy the particle experiences along that path over time. Once we know the action for a particular path, we assign to that path a phase factor, which is the exponential of I times the action divided by Planck's constant. This factor is a complex number with magnitude 1. You can think of it as an arrow in the complex plane pointing in some direction. Different paths correspond to arrows pointing in different directions. When we add up all these arrows, many of them cancel each other out, and only certain groups of paths contribute significantly. This is how classical mechanics emerges from quantum mechanics. When the action is very large compared to Planck's constant, the phase changes very rapidly from one path to a nearby path. As a result, the arrows corresponding to nearby paths point in very different directions, and they cancel out when added together. However, near the path for which the action is stationary, meaning that small variations of the path do not change the action much, the phases of neighboring paths are nearly the same. Their arrows point in almost the same direction, so they add up constructively. This special path is precisely the classical path given by the principle of least action. So in the limit where quantum effects become small, the path integral naturally reduces to classical mechanics. Now let us be more precise about what we mean by summing over all paths. Imagine that a particle starts at position x at time t and ends at position x prime at time t prime. We want to compute the probability amplitude for this transition. In the path integral formulation, this amplitude is called the propagator. The propagator is given by an integral over all possible paths that start at x and end at x prime. To make sense of this integral, we divide the time interval between t and t prime into many small slices. At each intermediate time, the particle can be at any position. So a path is specified by giving the particle's position at each of these intermediate times. We then integrate over all these intermediate positions. Finally, we take the limit in which the time slices become infinitely small. This gives us a continuous path. For each such path, we compute the action by integrating the Lagrangian along the path. Then we compute the phase factor associated with that action. Then we sum over all paths. The result is the propagator. Once we know the propagator, we can compute the wave function at later times from the wave function at earlier times. In this way, the path integral formulation reproduces the predictions of the Schrödinger equation. To see how this works in a simple example, consider a free particle, meaning a particle with no potential energy. Its Lagrangian is just its kinetic energy. The action for a given path is proportional to the integral of the square of the velocity. When we evaluate the path integral for this case, we find that the propagator has a simple Gaussian form. This result agrees exactly with what we get by solving the Schrödinger equation for a free particle. So even though the two approaches look very different, they give the same physical predictions. Another important example is the harmonic oscillator, a system where the force is proportional to the displacement from equilibrium. This system plays a central role in physics because it is a good approximation for many real systems near stable equilibrium. When we evaluate the path integral for the harmonic oscillator, we again find a result that matches the standard quantum mechanical solution. But the path integral method gives us additional insight into how the classical motion emerges and how quantum fluctuations around that motion contribute. One of the greatest strengths of the path integral formulation is how naturally it extends to systems with many degrees of freedom and to fields. In quantum field theory, instead of a particle moving along a path, we have fields that assign a value to every point in space and time. A configuration of the field is like a path, but in a much higher dimensional space. The action is now a functional of the field configuration, and the path integral becomes an integral over all possible field configurations. This is the foundation of modern particle physics. In this framework, interactions between particles arise from terms in the action that involve products of fields. When we expand the exponential of the action in powers of these interaction terms, we obtain a series of contributions that can be represented by diagrams. These diagrams, known as Feynman diagrams, are a graphical way of keeping track of the terms in the expansion. Each diagram corresponds to a particular process, such as two particles scattering, or a particle emitting another particle. The rules for drawing and evaluating these diagrams come directly from the structure of the path integral. The path integral also provides a deep connection between quantum mechanics and statistical mechanics. If we replace time with an imaginary variable, the oscillatory phase factor becomes a decaying exponential. This transforms the quantum mechanical path integral into something that looks like a partition function in statistical mechanics. This correspondence allows us to use techniques from one field to solve problems in the other. For example, properties of quantum systems at zero temperature can be related to properties of classical systems in one higher dimension. Another powerful aspect of the path integral formulation is how it handles symmetries. Symmetries play a central role in physics because they lead to conservation laws. In the path integral approach, a symmetry is a transformation of the paths or field configurations that leaves the action unchanged. When such a symmetry exists, it implies the existence of a conserved quantity. This is a direct expression of Noether's theorem. Gauge symmetries, which are fundamental to the standard model of particle physics, are most naturally described using the path integral. The path integral also gives us an intuitive picture of quantum tunneling. In classical mechanics, a particle cannot pass through a potential barrier if it does not have enough energy. In quantum mechanics, tunneling is possible. In the path integral picture, tunneling arises because there are paths that go through the classically forbidden region. These paths have an action that is imaginary, leading to an exponential suppression of their contribution rather than an oscillatory phase. This explains why tunneling probabilities are small but done-go. Philosophically, the path integral formulation suggests that nature does not follow a single history, but rather explores all possible histories. What we observe is the result of interference between these histories. This idea challenges our everyday intuition about cause and effect and about the uniqueness of events, but it fits naturally with the probabilistic structure of quantum mechanics and with the experimental evidence that supports it. In practical calculations, the path integral can be evaluated exactly only for simple systems. For more complicated systems, we use approximation methods. One important method is the Semizolocki approximation, where we expand around the classical path. Another is perturbation theory, where we treat interactions as small corrections to a simpler system. For strongly interacting systems, we often use numerical methods such as Monte Carlo simulations on a lattice. These methods are especially important in the study of the strong nuclear force. The path integral formulation also plays a role in attempts to unify quantum mechanics with general relativity. In such approaches, one considers a sum over all possible geometries of space-time. Each geometry has an associated action, and the quantum amplitude is obtained by summing over these geometries. Although this program is still incomplete, it shows how general and flexible the path integral idea is. In the coming parts of this series, We will go deeper into the mathematical structure of the path integral. We will derive it carefully from the Schrödinger equation. We will study explicit examples in detail, and we will explore its applications in quantum field theory and beyond. Step by step, we will build up the intuition and the technical tools needed to truly understand this beautiful formulation of quantum mechanics. As we continue our journey into the path integral formulation of quantum mechanics, let us now focus on how this idea can be derived more carefully from the standard formulation using the Schrödinger equation. This will help us see that the path integral is not just a poetic picture but a precise mathematical framework that is fully equivalent to ordinary quantum mechanics. We begin with the time evolution of a quantum state. In standard quantum mechanics, the state of a particle is described by a wave function, and its time evolution is governed by the Schrödinger equation. If we know the wave function at an initial time, we can calculate it at a later time using an operator called the time evolution operator. This operator can be written as an exponential involving the Hamiltonian of the system and the time interval. The probability amplitude for a particle to go from one position to another is given by a matrix element of this operator between position states. Now imagine breaking the total time interval into many very small pieces. Instead of evolving the system from the initial time directly to the final time, we evolve it step by step through these tiny intervals. At each step, we insert a complete set of position states. This means that at each intermediate time, we allow the particle to be at any position. Mathematically, this corresponds to integrating over all possible intermediate positions. When we multiply together all these short time evolution factors and then integrate over the intermediate positions, we obtain an expression that looks like a sum over all possible paths the particle could take. For each small time interval, the contribution to the amplitude depends on the kinetic and potential energy of the particle during that interval. When we multiply these contributions together and take the limit in which the time intervals become infinitesimally small, the product becomes an exponential of an integral over time. This integral is precisely the action. Thus we arrive at the central result. The probability amplitude for a particle to go from one point to another is given by an integral over all possible paths, weighted by the exponential of I times the action, divided by Planck's constant. This derivation shows that the path integral is not an alternative theory, but another way of organizing the same information contained in the Schrödinger equation. However, the path integral offers a very different perspective. Instead of focusing on the wave function at each instant of time, we focus on entire histories of the system. This shift in viewpoint turns out to be extremely powerful, especially when dealing with complex systems and interactions. Let us now think more carefully about what it means to integrate over all paths. A path is a function of time that specifies the position of the particle at every moment between the initial and final times. The set of all such functions is infinite dimensional. Integrating over this set is therefore very different from ordinary integrals over numbers or vectors. To make sense of it, we define the path integral as a limit of ordinary integrals over the positions at discrete times. This procedure is sometimes called time slicing. Each slice introduces an ordinary integral, and the path integral is the limit as the number of slices goes to infinity, and the size of each slice goes to zero. Although this definition is mathematically subtle, it works remarkably well in practice. For many systems, we can evaluate the path integral exactly or approximately. One of the simplest cases is again the free particle. Because the action is quadratic in the velocity, the integrals over the intermediate positions are Gaussian and can be done exactly. This leads to a closed-form expression for the propagator. Another instructive example is a particle in a constant force field. In this case, the classical path is a parabola. When we evaluate the path integral, we find that the dominant contribution comes from paths near this classical path. But there are also contributions from nearby paths that represent quantum fluctuations. The result again matches what we obtain from solving the Schrödinger equation directly. This idea of expanding around the classical path leads us naturally to the semizolical approximation. In this approximation, we write each path as the sum of the classical path and a small deviation. We then expand the action in powers of this deviation. To lowest order, the action is stationary along the classical path, and the next terms describe small oscillations around it. This leads to an approximate expression for the propagator that includes both the classical action and a factor representing quantum fluctuations. This approximation becomes more accurate when the action is large compared to Planck's constant, which is the regime where classical behavior dominates. The semizolical approximation also helps us understand phenomena like interference and diffraction. When there are multiple classical paths connecting the same initial and final points, such as in the case of a particle passing through two slits, each path contributes a phase determined by its action. The interference pattern arises from the superposition of these contributions. The path integral thus provides a natural explanation for wave-like phenomena in terms of the interference of different histories. Let us now turn to the role of the path integral in quantum field theory. In quantum field theory, the fundamental objects are fields rather than particles. A field assigns a value to every point in space and time. The evolution of the field is described by equations of motion derived from an action principle. To quantize the field using the path integral, we consider all possible field configurations and weight, each one by the exponential of I times the action divided by Planck's constant. This is the direct generalization of summing over paths for a particle. In this context, the propagator becomes the correlation function of the field. It gives the amplitude for a disturbance in the field at one point to influence the field at another point. Interactions between fields lead to terms in the action that are higher order in the fields. When we expand the exponential of the interaction terms, we obtain a series of integrals that can be represented by diagrams. These diagrams encode how particles are created, annihilated, and scattered. The path integral thus provides the foundation for the diagrammatic techniques used in particle physics. One of the most striking features of the path integral formulation is its ability to handle systems with constraints and symmetries. For example, in gauge theories, there are redundancies in the description of the fields. Many different field configurations correspond to the same physical situation. In the path integral, this leads to overcounting, unless we introduce a procedure to fix the gauge. This is done by inserting a constraint and a corresponding determinant into the integral. Although this procedure may seem technical, it is essential for obtaining correct results and preserving unitarity and causality. The path integral also clarifies the relationship between quantum mechanics and classical statistical mechanics. By replacing real time with imaginary time, we transform the oscillatory exponential into a decaying exponential. This turns the quantum mechanical path integral into a partition function that resembles that of a classical system. This correspondence is widely used in condensed matter physics, where quantum systems at low temperature can be studied using classical statistical methods in higher dimensions. Another important application of the path integral is in the study of topological effects. In some systems, there are paths that cannot be continuously deformed into each other. These different classes of paths can lead to distinct quantum phases. Such effects play a role in phenomena like the Aharonov-Bohm effect, where a particle is influenced by a magnetic field, even when it moves through a region where the field is zero. In the path integral picture, this effect arises because the action includes a term that depends on the electromagnetic potential, and paths that wind around a magnetic flux acquire different phases. We can also use the path integral to study systems with dissipation and noise by coupling the system to an environment. By integrating out the degrees of freedom of the environment, we obtain an effective action for the system alone. This effective action can include terms that represent friction and random forces. This approach is widely used in the study of open quantum systems and quantum decoherence. Decoherence itself can be understood naturally in the path integral framework. When a system interacts with its environment, different paths of the system become entangled with different states of the environment. When we sum over the unobserved environmental degrees of freedom, the interference between certain paths is suppressed. This leads to the emergence of classical behavior for macroscopic systems. Thus, the path integral provides a bridge between the microscopic quantum world and the macroscopic classical world. As we move forward, we will explore more detailed calculations using the path integral, including explicit evaluations for specific potentials and the treatment of interacting systems. We will also examine how the path integral approach leads to powerful conceptual tools, such as effective actions and renormalization. Step by step, we will build a deeper understanding of how this formulation unifies many areas of physics and provides insight into both the mathematics and the philosophy of quantum theory. As we move deeper into the path integral formulation, it is time to focus more carefully on how actual calculations are performed and what physical meaning we should attach to the results. Until now, we have spoken in general terms about summing over all paths, but to really understand this idea, we must see how it works, step by step, and how it connects to measurable quantities. The central object in the path integral approach is the propagator. The propagator gives the probability amplitude for a particle to go from an initial position at an initial time to a final position at a later time. Once we know the propagator, we can determine how any initial wave function evolves with time. The propagator itself is given by the path integral over all possible paths that start and end at the specified points. Each path contributes a phase factor that depends on the action along that path. To evaluate this expression, we imagine dividing time into many small intervals. At each intermediate time, the particle can be anywhere in space. We integrate over all these possible positions. When we multiply together the contributions from each small time step and then take the limit where the number of steps becomes infinite, we obtain the full path integral. Although this procedure may sound abstract, it is very similar to how we define ordinary integrals as limits of sums. For many systems, the action is a simple quadratic function of the coordinates and velocities. In such cases, the path integral reduces to a Gaussian integral, which can be evaluated exactly. This is why the free particle and the harmonic oscillator are so important. They serve as test cases where we can see the path integral in action and verify that it gives the correct results. For a free particle, the classical path is a straight line connecting the initial and final points. When we evaluate the path integral, we find that the dominant contribution comes from paths close to this straight line, but all other paths also contribute in a way that ensures the final result matches the solution of the Schrödinger equation. The propagator for a free particle has the form of a spreading wave packet, which reflects the fact that a localized particle becomes more uncertain in position as time passes. For the harmonic oscillator, the classical path is a sinusoidal motion. The path integral again shows that the dominant contribution comes from paths near this classical motion. However, the quantum result also includes fluctuations around this path. These fluctuations are responsible for the zero-point energy of the oscillator, which is the fact that even in its lowest energy state, the oscillator does not sit perfectly still. This brings us to the concept of quantum fluctuations. In the path integral picture, quantum fluctuations arise because we are summing over paths that deviate from the classical path. These deviations represent small random motions that have no counterpart in classical physics. Even when a system is in its ground state, these fluctuations are present. They are a direct consequence of the uncertainty principle and the wave-like nature of quantum systems. Another powerful idea that emerges naturally from the path integral is the notion of an effective action. In many problems, we are not interested in every microscopic detail of a system. Instead, we want to describe its behavior at large scales. By integrating over certain degrees of freedom, we can obtain an effective action that describes the remaining degrees of freedom. This effective action includes the effects of the eliminated variables in an averaged way. This technique is widely used in quantum field theory and condensed matter physics. The path integral also provides a natural framework for perturbation theory. Suppose we have a system whose action can be written as the sum of a simple part and a small interaction part. We can treat the interaction part as a perturbation and expand the exponential of the action in a power series. Each term in this expansion corresponds to a particular way in which the interaction can occur. These terms can be represented graphically by diagrams which help us organize and compute the contributions. The rules for constructing and evaluating these diagrams follow directly from the structure of the path integral. In addition to perturbation theory, the path integral allows us to study non-perturbative effects, which are effects that cannot be captured by a simple power series expansion. One important class of non-perturbative effects is associated with special paths called instantons. Instantons are solutions of the equations of motion in imaginary time. They represent tunneling events between different classical states. In the path integral, instantons appear as particular paths that make significant contributions to the amplitude. They play a crucial role in phenomena such as barrier penetration and certain effects in quantum field theory. Let us now turn our attention to the role of the path integral in understanding measurement and decoherence. When a quantum system interacts with a measuring device or with its environment, its different possible paths become correlated with different states of the environment. When we sum over the environmental degrees of freedom, many of the interference terms between different paths are suppressed. This leads to a situation where only certain paths remain relevant, and the system behaves more classically. In this way, the path integral provides a natural picture of how classical behavior emerges from quantum mechanics through interaction with the environment. This picture also sheds light on the arrow of time. Although the fundamental equations of quantum mechanics are time-symmetric, the process of decoherence introduces an effective direction of time. as the system becomes entangled with its environment. Information about its phase relationships is lost to the environment, and interference between different paths becomes negligible. This gives rise to irreversible behavior at the macroscopic level, even though the underlying laws are reversible. Another fascinating application of the path integral is in the study of topological phases of matter. In some systems, the properties of the quantum state depend not on local details, but on global features of the paths or field configurations. These topological properties are robust against small perturbations and play a role in phenomena such as the quantum Hall effect and topological insulators. In the path integral language, these effects arise because certain classes of paths contribute distinct phases that cannot be removed by smooth deformations. The path integral also helps us understand anomalies, which are situations where a symmetry of the classical action is not preserved after quantization. In the path integral framework, anomalies arise because the measure of integration over paths or fields is not invariant under certain transformations, even if the action itself is. This insight has profound implications for particle physics, as it determines which theories are mathematically consistent and which are not. We can also use the path integral to study systems out of equilibrium. By extending the formalism to include complex time contours, we can describe how systems evolve when they are driven by external forces or when they are suddenly changed. This approach is especially important in modern condensed matter physics, where experiments often involve rapid changes and strong driving. As we progress further, we see that the path integral is not just a method for solving problems. It is a way of thinking about physical reality. Instead of imagining a single history, we imagine a vast collection of possible histories, all contributing to what we observe. The laws of physics determine how these histories are weighted and how they interfere with one another. The classical world emerges as a special case, where one history dominates. This perspective also invites us to reconsider the meaning of probability in quantum mechanics. Probabilities do not arise because nature is ignorant of what it is doing. They arise because the outcome of a process depends on the interference of many possibilities. The path integral makes this explicit by showing how each possibility contributes a complex amplitude, and how these amplitudes combine to produce observable probabilities. In the next part of this series, we will examine more specific mathematical tools used in the path integral approach, such as functional differentiation and generating functionals. We will also look more closely at how correlation functions are computed and how they relate to physical observables. Step by step, we will continue building a detailed and intuitive understanding of this powerful formulation of quantum mechanics. As we reach the final part of this long discussion, let us now bring together all the ideas we have developed and reflect on what the path integral formulation really teaches us about quantum mechanics and about nature itself. We have seen that the path integral approach replaces the idea of a single definite trajectory with a sum over all possible histories. Every possible path contributes to the final result, and each contribution is weighted by a phase determined by the action. This simple rule contains within it the entire structure of quantum mechanics. From it, we can recover the Schrödinger equation, the principle of superposition, interference, tunneling, and even the emergence of classical motion. One of the most profound lessons of the path integral is how naturally it unifies different areas of physics. Classical mechanics appears as a limit in which only paths near the stationary action contribute significantly. Quantum mechanics appears when many paths interfere. Quantum field theory arises when we generalize from particle paths to field configurations. Statistical mechanics emerges when we rotate time into the imaginary direction. In this sense, the path integral is not just another formulation of quantum mechanics. It is a unifying language that connects many seemingly separate theories into a single framework. Another important insight is the role of phase. In classical physics, only energy and forces matter. In quantum physics, phase is just as important as magnitude. Two paths with the same action can reinforce each other, while two paths with different actions can cancel each other out. The path integral makes this idea central. It tells us that what matters is not just which paths are possible, but how their phases compare. Reality, in this view, is shaped by interference between alternatives. This also gives us a new way to think about causality and determinism. In classical physics, the future is determined uniquely by the present. In the path integral picture, the future is not determined by a single path, but by a weighted sum of many possibilities. What we can predict are probabilities, not certainties. Yet these probabilities are not arbitrary. They arise from a precise mathematical structure based on the action. Chance and law are not opposites here. Chance itself is governed by a strict and elegant rule. We have also seen how the path integral helps us understand phenomena that look mysterious in other formulations. Tunneling becomes the contribution of paths through forbidden regions. Zero-point motion becomes the effect of quantum fluctuations around classical paths. Decoherence becomes the suppression of interference between different histories when a system interacts with its environment. Even the arrow of time can be linked to the loss of phase information into the environment. In practical terms, the path integral is one of the most powerful tools in theoretical physics. It underlies the calculation of scattering amplitudes in particle physics, the study of phase transitions in condensed matter systems, and the investigation of non-perturbative effects such as instantons and solitons. It allows us to use diagrammatic techniques to organize complex calculations and numerical simulations to study systems that cannot be solved analytically. Without the path integral, much of modern physics would not exist in its current form. But beyond its technical power, the path integral offers a deeply poetic view of nature. Instead of a single story, the universe contains an infinity of stories. Every possible history plays a role in shaping what actually happens. What we observe is the result of a grand interference pattern formed by all these histories. The classical world, with its definite objects and trajectories, emerges from this quantum sea of possibilities through constructive and destructive interference. This way of thinking also changes how we view the concept of reality. It suggests that asking which path a particle really took may not be a meaningful question. What is meaningful is the total amplitude resulting from all paths. Reality is not built from individual histories, but from the sum of all histories. This challenges our everyday intuition, but it fits perfectly with what experiments tell us about the quantum world. So when we think about a particle traveling from one point to another, we should not imagine a tiny object moving along a single line. We should imagine a vast collection of paths, each one contributing its own tiny whisper to the final outcome. The motion we see is the result of all these whispers combined into a single voice by the rule of the action. In this long series, we have moved from the basic idea of summing over paths to its deep connections with classical mechanics, quantum field theory, statistical physics, and the foundations of measurement and decoherence. We have seen that the path integral is not just a computational trick. It is a conceptual framework that reveals the unity of physics and the subtle way in which possibility becomes reality. And with that, we come to the end of this section on the path integral formulation of quantum mechanics. A formulation that shows us that nature does not choose a single path, but explores them all, and from their interference builds the world we observe. If you like my video, please subscribe my YouTube channel for more videos. In the next part of this series, we will examine more specific mathematical tools used in the path integral approach, such as functional differentiation and generating functionals. We will also look more closely at how correlation functions are computed and how they relate to physical observables. Step by step, we will continue building a detailed and intuitive understanding of this powerful formulation of quantum mechanics.